Now, we've been looking at some optimization problems, and we're getting into some very heavy problems dealing with problem solving, word problems, applications, whatever you want to call them. And no matter what level of mathematics we're at, this seems to be the hardest thing that we do in that class. So we're going to kind of step back and look at some ways, maybe a little bit different description, a little more explanation into problem solving. And again, there's a long list of different ways to explain this, but hopefully what we'll do today will help you to understand it a little bit better, to be able to perform the problem-solving techniques on the questions, on the activities we do. So, first thing I would do, now, I guess this would fall under the first part, but read the question and maybe read the problem 2 or 3 times. Okay, you got to have a good understanding of what's being asked, and reading through it quickly just once, you're going to miss some details. So read. I am a very slow reader, and maybe this is why, is because I've got to read every little detail to make sure I've got it. Even reading for enjoyment, which I don't really know what reading for enjoyment is, because when I read, it's not really enjoyment, but I'd rather play a video game or something like that for enjoyment. But anyway, some people read for enjoyment. But read the problem, read it carefully, maybe read it 2 or 3 times, okay? And one thing he points out in our videos, we need to understand what's being asked. Okay? And that you can kind of sift through all the information. We need to pick out what is the question being asked. So identify what is that question. Now, sometimes the question, especially with our problems, we can create an equation or at least a verbal model. Maybe area equals length times width, or maybe it's area of a rectangle plus the area of a circle. Okay, that equals the total area. Something like that, where we can identify this is the equation that we're going to be dealing with, and maybe the equation involves just wording, but then from there, number 2, we can start filling in the information that we know. So determine what information is given, what do we know about the problem. Okay, and in this part, one thing that really helps me is to draw a picture. Now, you guys haven't been blessed to see my artistic ability or lack thereof, but when I say draw a picture or a diagram, I'm usually talking about straight lines, maybe trying to draw a circle or something that we assume is a circle. I can draw at least somewhat decent on that, but draw out a picture, a line, points, a triangle, something like that, to give us an idea of what we're talking about. And then from the description, okay, maybe the length is described in terms of the width. Show the relationship there. Or maybe we need to say, let the length be x and the width be y, and then the perimeter, I'll write down the perimeter if it's a rectangle, P equals 2L plus 2W. Put in the number, if we're given the perimeter, put in the number for P, and then X for the length and Y for the width. Okay. Sometimes we're given information that we can organize in a table. If we have several different parts or even two parts that we're going to add together to make a total, sometimes we can identify different pieces of the first part, different pieces of the second part, and then how we can add those pieces together to get our total. So a lot of different ways to help us out in determining what information we know, pictures, diagrams, tables, okay? And a lot of that is, that's a very general technique. It depends on what type of problem we're dealing with. But definitely pictures, even lines and dots. I can draw a line and a dot. Maybe it's not a real straight line, but at least it's a line. Okay. And then once we kind of organize that information, figure out what we know, then we come back to 1 and kind of try to tie 1 and 2 together. What do we know, and what are we trying to find out? How are they related? Okay. If we want to know the area of something, then we need to know the length and the width, and maybe in part 2 we found out from the perimeter that the length was twice as much as the width, or something like that. Some relationship from what we know. We can then, a lot of times it's a matter of just substituting one variable from the known information. We might get an equation with two variables, solve the equation for one of those variables, and then substitute it back into that equation we found at the beginning. Okay. So a lot of times that will get us down to where we're dealing with a function of just one variable. And that's, especially in the optimization problems, that's what we're looking for. We need to get a function of just one variable that we can say, okay, what will maximize this function or what will minimize this function? And then we can start going through the calculus once we get to that point. Once again, it's not necessarily the calculus that's hard, it's all the algebra leading up to it. And in this case, a lot of problem solving leading up to it. Okay? Well, let's use this this problem-solving technique to answer a question, and I'm going to refer back to yesterday's worksheet, problem number 7. I know that I get a lot of questions on that one. It's not the exact same setup as all the other problems, so this one takes a little bit of thought, and it's real good to kind of go through those problem-solving steps that we talked about. Okay. So first up, read the question. Rectangular page is to contain 30 square inches of print. There is to be a border of 1 inch around all sides. What are the dimensions of the page that will use the least amount of paper? Okay. So, what are we asked to find here? What is the question? The dimensions of the page can be represented length and width. And more specifically, we need to look at the rest of the question. The dimensions of the page for what? Using the least amount of paper. Least amount of paper means what in more mathematical terms? Okay, the minimum, what's square inches?
Area.
Minimum area. So that might be something we need to kind of rewrite. Again, a lot of these words are very similar in nature, but least amount of paper, when we see that, we're like, okay, what's that relate to? But when we see area and we're talking about a rectangle, hopefully an equation pops into mind right away. So the verbal model then, area would equal what? Length times width. Okay. So we have a very basic equation that we're going to try to kind of fill in the missing pieces to be able to work through the problem. Okay. Now, how are we going to work through this? What else do we know? Well, one thing that always helps, find the actual numbers that we're dealing with. The 30 square inches of print. Okay. Now, here is where we may want to draw a picture. And I think I'll move on to the next page. Here's a rectangular page, and we're told 30 square inches of print, but what else are we told about the problem? We're told that we need a border of 1 inch all the way around. So, well, the print is to be here in the middle of it, but the border is not to have any print on it whatsoever. Okay. So, let's see, this much we would have 1 inch. Here we would have 1 inch. This side we'd have 1 inch. Here as well. So all the way around we have 1 inch. And we're also told this area in here would be what? Okay, this is to be the 30 square inches. Okay. Well, our length and our width is, for the page, is what we're looking for. And we can call that L and W. But where we're also told the area of the inside, okay, we're kind of looking at two different areas here. The area of the printed page and then the area of the entire page. Border with the print. So we may want to represent these length and width of the printed page as something else as well. And let's go ahead and say the printed part will be X and Y. So sometimes we have to say, okay, we're going to define this piece as X or this piece as W, and then go from there and define all of our terms in with variables or algebraic expression. Okay. Now, ultimately, we're wanting length and width defined. But given our area of the printed part, the 30 square inches, that's not length and width, that's the x and the y. However, once we define x and y, we could say x and y are related how?
Because if you multiply them together, they give you the area of each side.
Okay, the 30 square inches, the area of the printed part, is going to be represented now as the x times y. So the length times width of the printed part, x times y, would give us the 30 square inches. Okay. Now, what about the length and the width? How can we represent L with what we have done so far?
Could we just do x plus 2?
Okay, exactly. The length from here to here, well, this much is x. And then we have 1 inch here and another inch here. So the length is going to be x plus 2. What about the width? Okay, width will be y plus 2. That's an equal sign, not a z. Almost looked like a z there. So we have now length and width represented in terms of our x and our y. So as we kind of pull this back to our question, the beginning we had said area was going to equal length times width. Now we can say the area will be length times width. Well, we're still describing area of this page in terms of two variables, okay? But we want it in terms of just one variable. But what we found out earlier, what does x and y, how are x and y related? We said the x times y equals 30. So from that equation, that relationship between the two parts we want to know, we can solve one of those, solve this equation for one of the variables. Doesn't matter which one. We could solve for x if you want, but in this case we'll solve for y. Y is going to be 30 divided by x, and then we can substitute that in here. So our area of this page now we can say is a function of just our one variable x, and that's going to be the binomial x plus 2 times another binomial 30 over x plus 2, which comes from the y plus 2. Okay. And now we're ready to do the calculus. Now, like many times, it's easier to do some algebra, some more algebra, simplifying the expression before we do the calculus. That might be the case here. Let's go ahead and multiply the binomials before we do any calculus on it. So x times 30 over x, well, x divided by x will cancel. Then we'll have plus 2x, then plus a 60 over x, and then finally plus 4. Or the function, the kind of simpler form of this, combining our 30 and the 4 at the end, 34 plus 2x plus 60 divided by x, or we can go ahead and write that as x to the negative 1. Okay. So now we're going to be looking at this as a function representing the area of this page with the border around it, with the printed part. We want to minimize that area. And how do we minimize a function? We minimize this function by taking the derivative of it, and in this case that would be what? Okay, that'll be 0, derivative of 2x, and then derivative of 60x to the negative 1, negative 1 x to the negative 2. And what do we do with that derivative then, with that equation? Okay, minimize or maximize. It's where the derivative equals 0. So set this function equal to 0. And let's see, let's go ahead and rewrite this part a little bit. 60 over x squared, and with the minus. Solve this equation for x. Well, with the 0 over here, I would add our 60 over x squared on both sides. Multiply x squared. And divide by 2. So x squared equals 30. X is going to be what? Well, yeah, whatever the square root of 30 is. Don't know that one right off the top of your head? Me neither. But anyway, x would be exactly the square root of 30. Now, in practical terms, we're not going to want to write the answer as square root of 30. Out in the real world, you're not going to say, well, the length of this wall needs to be square root of 30 feet. Well, no, we can calculate a decimal value, probably around 1 or 2 decimal places. Depends on I always look at what the result is and what would be a nice decimal place to round to. But is that exactly what we're looking for? X represented what? The length of the printed part. So the length of the page we wanted is x plus 2. So it'd be square root of 30 plus 2. Okay. And then y, well, we'll put it this way. The other part we need is w, which would be y plus 2. What did we say y was?
30 over x.
Okay. 30 over x, which, well, again, those are the exact values. When you plug that into your calculator, and when you do that, be very careful. Make sure you get parentheses around that. 30, okay, because we're looking for the width of the page, not just the printed part. Y represents the width of the printed part, and then plus 2 for the border. Okay. And, yeah, okay. Oh, yep. This should not be the plus 2. Right? Okay. 30 over x, not 30 over L. That's another thing you got to be real careful with. Okay, so 30 divided by square root of 30 plus 2. Okay, those little mistakes kill you. Thanks for catching mine. I still make them. calculate that, and we get our length then as, well, approximately what? Somebody have that decimal value? So square root of 30 is about 5.477, and then plus 2, so 7.477. And what units were these? Inches. And then the width, well, that value actually turns out to be the same, 7.477 inches for the width. So for this particular problem, the way to minimize the amount of paper used would be to make it a square. Okay, so that's kind of a little bit different approach, or a little bit more detailed approach of how to look at these application problems. Hopefully that'll give you a little better idea of how to approach some of our worksheet problems.